Now let's discuss how to apply the superposition method to statically indeterminate problems. So let's consider the problem that I introduced in previous lecture. So this is typical problem involving redundant support, and due to this redundant support, we have three unknowns, even though we have two mechanical equilibrium equations. So that we cannot solve this problem by statics analysis only. Okay, so we have to use the information about deflection. So instead of solving the problem as I introduced in previous lecture, where we use 5 unknowns in addition to 3 unknowns here, we have 2 unknowns from integration constant, and we have to find the 3 more boundary condition equations. Here, let's try to adapt the superposition principle. So if I convert this problem, instead of this decomposition, we can simply replace this redundant support with force reaction FB. Okay, so we have only one unknown. This is unknown. Now let's split this problem into two problems, first problem and second problem. And first problem, we already know the solution for problem A. For problem B, we know the solution even though we don't know what's the value for FB. So even though it's still unknown, we can describe the solution for problem B in terms of FB by looking up the table in appendix. Okay, so for problem A, we're gonna have the downward deflection. For problem B, we're gonna have upward deflection. However, if we combine deflection at these 2 points, they must be summed up to be 0 to have a same boundary condition with the original problem. Okay, so we have so-called compatibility condition. To be compatible with the original problem, solution of YA and solution of YB and their deflection at x equal L point must to be summed up to be 0. Okay, so this is additional equation, and we know the solution for B problem in terms of FB, so we can obtain the solution of original problem. So the A problem has this curve, and B problem have this curve. Okay, so if you let me see, plug in x equal L, here x equal L, then this is what you get at the deflection at the end of the beam. And for problem B, if you plug in x equal L, this is the deflection that you're gonna get about problem B. Then our compatibility condition tells us that if you sum up this guy and this guy, they must be summed up to be 0. Okay, and FB is the only unknown, and L, E, I, and W, these are the values given in the solution. So we can obtain FB in terms of others, and we can define FB in terms of these values. We know the solution for YB now. Then the solution for original problem is YA plus YB for entire region. Okay, so this is how we utilize the superposition principle. Instead of worrying about 5 unknowns and 5 coupled equations, we can only have just one additional equation to find one additional unknowns. Okay, so this is how we approach the problem using the known solution of simple problems. Now let's move on to a second problem. So here we're gonna have a little bit more complex problem. So in this problem, we have redundant rigid wall. Due to redundant rigid wall, we have 2 additional reactions, FC and MC. Without FC and MC, we can make a mechanical equilibrium, but we are adding some additional moment and force due to rigid wall at the right end. Okay, so there are 4 unknowns in this problem to determine the reaction from the wall. However, we can have only 2 equations from mechanical equilibrium, so we have to find a lot of boundary conditions. However, let's try to use the superposition method and try to design a solution how to solve this problem. So here we can decompose the problem into many small problems. So instead of replacing the left wall with unknown MA and FA, let's keep left wall, and decompose the problem into 3. So for right wall, we're gonna have FC and we're gonna have MC. However, because we have the solution for a single FC and single MC, we can split the problem into three parts. First part, second part, known solution in the appendix, C part. So this is known, we have known solution here, we have known solution here, because we have known solution, given as this. Okay, now regarding this problem, we have known solution up to this point, and we have to determine AXB, but we have the solution for this guy from page 3. Okay, where is page 3? This is our solution yx for entire region by determining A and B. Okay, so because we can decompose the original problem into three problems where the solution is known to us, it's our job to determine what is the appropriate compatibility equation. So here the complexity we have is, in previous page we have only one unknown, but here we have two unknown, FC and MC. Given two additional unknown, we have to find two compatibility equation. However, actually we can find two compatibility equation quite easily, because original problem considers residual at the right end. At the right end, then it means that y x equal a plus b should be 0, and dy dx evaluated at x equal a plus b must be 0. Okay, so these are the compatibility equation to satisfy the boundary condition of original problem. So what we can do is, we have to consider dy dx, we have to consider y itself at the right end. Okay, so at the right end, if you sum up dy dx for a problem, b problem, c problem, they should be summed up to be 0. At the right end, if you obtain the deflection of a problem, b problem, c problem, it should be summed up to be 0. So we have two additional equation, we have two unknowns, and we can find the solution for FC and MC. After defining FC and MC, we know the solution for A, B, and C. After summing up all solution, we're gonna be able to answer the original problem elastic curve. Okay, so this is how we can apply the superposition method, and by applying the superposition method, and given this set of known solutions, we can find a lot of complex problems with combined loading with relatively simple procedure to get the final solution. Okay, so with that, let me finish my discussion on beam deflection using force and moment equilibrium and other method. And in the next lecture, we'll finally get into a new mode instead of relying on Newton's second law. Actually, Newton's second law is given in these conditions. Instead of using Newton's second law, F equal ma, and Newton's third law, which is F, the action reaction principle, without using the those force equilibrium law, in the third how can I say, in the new chapter, instead of a force method and those equilibrium method, we're gonna use energy method to solve the beam deflection problem. Okay, so you're gonna get into, and you're gonna get exposed to a relatively new concept of the lectures, and new, I would say, entertainment, I would say. Okay, so let me stop here and see you in the next lecture.